We add a new experiment for the pad cell with graphite against lithium metal. We add a cell group with a single cell, give it the name of the ingredients of this pad cell. So it's graphite against lithium with a lithium metal ring-shaped reference electrode. We assign the script we have just written. We check the cell composition. So the upper electrode is lithium foil and the lower electrode is graphite. It's just the same we have used in the previous experiment, so we don't have to change that here. And then we go into the assembly view, put in the weight of the graphite electrode, 0.02, and enter the cell tag, which is A0001. Then we assign it to the channel where we have inserted the pad cell. The tester used here is a staging tester, and it was inserted in channel number 1. So it is this channel, and then we start the measurement. We go into the viewer. First, the channel board is being calibrated during the first few seconds, and then the script starting with an open circuit period of 20 seconds. Here we see the incoming data. So first step is open circuit. Here you see a sketch of the cell with the ingredients. The upper electrode 2 is lithium foil, the lower electrode 1 is graphite, and the insulation sleeve is with a lithium ring. We change the graph layout into 2 columns. So we are now in the galvanostatic impedance step. I add a graph where I plot the Nyquist diagram from the output impedance table on X. We plot the real part of the full cell impedance, on Y the imaginary part of the full cell impedance, and we add the frequency as a label here. So here you see the incoming impedance data. The spectrum is now finished, and we are in the constant current, in the lithiation step. So a current of -1 milliamp is being applied, and after 300 seconds the impedance is measured at this bias current for the first time. We add another graph in order to plot the half-cell impedance of the graphite electrode. So from output impedance we plot on X the real part of Z1, and on the Y-axis the imaginary part of Z1, and add the frequency as a label here. So this is the spectra of the graphite electrode before the lithiation has started. And we add another diagram where we plot the impedance of the lithium metal counter electrode. this is now the real part of Z2, and on Y the imaginary part of Z2 and the frequency again as a label. And you see automatically the diagram is shown as a Nyquist diagram. So same scaling on X and Y axis, and the direction of the Z axis is inverted. So negative values go up. We change the graph layout in order to see all the diagrams like that. And that way you can use a much bigger screen and show many diagrams side by side. With the cursor you can go through one diagram and see the corresponding change in the other diagrams. So the diagrams are linked time-wise. After about 6 minutes, the impedance is being measured the first time with a bias current of -1 milliamp. You see the spectra building up here in this Nyquist diagram, and the same here for the two half cells, for the graphite electrode, this one, and for the lithium metal counter electrode. You see the semicircle here for the SEI on the lithium metal. You see how much this has decreased since the very beginning, and you see the dramatic change in the graphite spectra only after applying a constant current of -1 milliamp for 5 minutes. After about 13 hours, the first cycle is completed, and we see here now many impedance spectra for the full cell and the two half cells. And you see this is no longer a good way to interpret the impedance data. We will therefore do that in a different way now. I minimize those diagrams and add another graph where I plot from the output impedance table as a function of the time, the magnitude of the full cell impedance, and the same for the two half cells, for Z1 and Z2. We have a closer look on those two diagrams, the voltages and the impedances, and for that purpose we changed the graph layout into just one single column. I move that diagram up here. Okay, and here you see the evolution of the impedance data in the lower diagram. Initially, during the first half cycle, we dissolve the fresh lithium metal and only leave a smooth lithium metal surface behind. So during this time period, about 7 hours, the lithium has a small surface area and so a high impedance because it's covered with the SEI layer, and this can be seen here. So at low frequency, the upper point of the envelope of the blue curve, this is for low frequency, and you see this large impedance here, much bigger than the impedance of the graphite electrode. And only when we change the sign of current, when we start to delithiate the graphite and put the lithium as a dendritic porous layer on top of the lithium metal electrode, then the impedance of the lithium metal counter electrode is steeply dropping. And this fact can also be seen in the overvoltage of the lithium metal electrode. We go into this diagram and enlarge the y-axis. And now you can see the pretty high overvoltage for the lithium metal electrode during dissolution of lithium metal. And then here at the turning point where we change the sign of the current, initially still the overvoltage is high with different sign of course, but then is dropping. Look at the blue curve here. So from almost 30 millivolts down to 5 millivolts or so. And the same thing is reflected here in the blue curve. What you can also see in this diagram is the nice plateau, the nice plateaus in the half cell voltage of the graphite electrode, red curve, and the difference between the gray curve, full cell voltage, and the half cell voltage due to the overvoltage at the lithium metal electrode. And this is especially important at the vertex point of the cycle. So in the script we have defined as a vertex point when the graphite half cell voltage is 5 millivolts, then change the direction of current. And you see this pretty significant difference between the red curve and the gray curve. So it makes some difference whether you control the full cell voltage, the gray curve, or the graphite half cell voltage, the red curve.